So we are glad to have Hirosi Ooguri today, which is one of the recipients of this year Frontier of Science Award for field theory and string theory. And he will talk about constraints of quantum gravity. We can congratulate.
Thank you. Thank you for the very kind introduction. So can you hear me? Okay. So it's a great honor to receive this Frontiers of Science Award. It's particularly, I'm particularly pleased for two reasons. One is that yesterday I saw the list of other recipients, and they are wonderful people with great work. So I'm very honored to share the prize with them. And another is that the prize is given to my paper with Daniel Harlow, which we published 3 years ago, and on the symmetry of quantum field theory and gravity. And this has been one of my favorite recent papers, so I'm very happy to have this award. And so today I'd like to talk about not only that, but in some broader context of putting constraints on gravitational effective theory in low dimensions. So for gravitational system, there are no obvious constraints on low energy effective theory. It has become clear recently. So the question I would like to pose is how we can identify and derive them from the first principle of quantum gravity. And I will today present a proof of concept that we can actually do something like that in principle. And so the lesson is that there are more chairs in front if we want to sit. It is often said that the low energy effective theory is a way to parameterize our ignorance. We don't know the ultraviolet theory, but in low energy theory, we may not have to know about the ultraviolet theory in detail. You just write down all possible terms. But in the gravitational theory, sometimes if you just do run arbitrary parameterization, then you might be parameterizing an empty set. So you have to be careful. You can have a wonderful theory about low energy effective theory, which turned out to be describing empty set, and that's not very interesting. So that's a kind of a lesson that I would like to draw from this talk. So I repeat myself. So for gravitational systems, we can write down any low energy effective theory and expect that it has a consistent ultraviolet completion. But this is not the case with gravity. The separation of ultraviolet and infrared degrees of freedom that are very important for this idea of low energy effective theory fails with gravity. So for example, the radius of black hole horizon grows with energy. So this is contrary to the expectation that if you look at the high energy behavior, then you look at short distance behavior. The black hole behaves differently. So this leads to the idea that for gravitational system, there are constraints on the low energy effective theory that cannot be captured by the standard Wilsonian paradigm. And so this is the Cumrun Vafa in 2005 gave name for this kind of thing. So distinction between landscape and swampland. So I've been interested in understanding how to delineate a boundary between the landscape and the swampland. So today I would mainly talk about these two types of constraint. One is absence of parameter in low energy theory, and you can sharpen this requirement and also quantify it by formulating it as a distance conjecture. I put some years over here when, as far as I can go back, I can trace when this was first pointed out. And the absence of global symmetry is related to the citation of the awards this time. And we can quantify this to talk about the weak gravity conjecture. So today I will mostly talk about these two types of constraints. I'm going to explain that. So the swampland condition on low energy effective theory of gravitational systems motivated by a variety of circumstantial evidences. First, property of string worldsheet, string compactification, and the property of quantum black holes. But in this talk, actually, I would like to prove, I see there are some mathematicians, so I have to be careful, but prove in the sense of, in the rigor of theoretical physicists, for gravitational system in untilted space using ADS-CFT correspondence as the first principle. So we're going to translate this in the language of conformality theory and then prove them. Okay, so absence of parameters and quantify that to do the distance conjecture. So here is an answer to Edward's question. So as far as I can see, the first literature on the absence of Swampland condition is the autobiographical note of Albert Einstein, published in 1949, in which he had a very interesting section where he explained the notion of natural unit. Namely, he said that if you measure objects in terms of units natural to fundamental physical principles, such as Planck constant, Newton constant, etc., then he said that everything can be expressed in terms of dimensionless number. And so he said that then, so I'm quoting him, then only dimensionless constants could occur in the basic equation of physics. But then he said that concerning such, I would like to state a theorem, which at present cannot be based upon anything more than upon a faith in the simplicity, namely intelligibility of nature, that there are no arbitrary constants of this kind. Okay, so I claim that this is the first citation on the Swampland. So is there a modern formulation of this Einstein's claim, which is a conjecture zero of my paper with Cumrun in 2006. There we say that every parameter in quantum gravity is an expectation value of dynamical field and can be varied by changing its expectation value. Okay, in the context of ADS-CFT correspondence, there is actually almost a proof of this statement. So the proof goes in the following way. Suppose there is a continuous parameter in untilted space. So if we have a gravitational theory with parameter, then there must be a corresponding parameter in dual conformal field theory. And in such a conformal field theory, each parameter is associated to exactly marginal operators, which then correspond to massless scalar field by ADS-CFT correspondence, or the formation of the boundary condition at infinity. So this means that the continuous parameter, if the ADS Lagrangian density has a continuous parameter, there must be the corresponding massless scalar field, and the parameter is given by its expectation value. Okay? This is almost a proof, except that there is one assumption, which is that if you have a continuous family of conformal field theory, then there is actually exactly marginal operator which generates this. This is actually, as far as I know, this is actually a hypothesis. And in fact, currently I'm working with Yuya Kusuki and Shota Komatsu, where we're actually trying to derive this claim using just purely CFT statement. But I think this is a commonly accepted expectation. So assuming that, then this is almost a proof. Okay. However, this is not a very useful in low energy theory. Useful by which I mean that if you give me Lagrangian, I can tell you whether it's describing empty sets or not. And this is not useful because what appear to be parameter in low energy effective theory may be fixed by potential or a more fundamental high energy theory. So even if the low energy theory have seemingly some dimensionless parameter, by itself it may not say that it's in swampland. For example, we know that the standard model of particle physics has 18 parameters, and the lambda CDM model has 6 parameters. But we are not going to claim that they are in swampland yet. And because these parameters may correspond to some dynamical field, but its expectation value may be fixed. So, so this by itself is not a very useful way. So if we want to be able to tell when you look at the Lagrangian whether it's in swampland. So this is not by itself useful. So Cumrun and I try to sort of formulate conjecture that are useful in that sense. So that means that we have to go way outside of our comfort zone. So what seems to be rather sort of scarce set of evidence at the time, we made a few more conjectures. One was that there is always an infinite distance direction, which more precisely says that in conjecture 1, that if you choose any point in the moduli space and any positive number, there is always another point where the distance is bigger than that number. And the second conjecture is that if you go in that direction, there is actually a tower of light particles. That is to say that compared to the effective theory at a given point, if you go further distance and distance greater than t, then an infinite tower of light particles starting with the mass of order exponential minus alpha t for some alpha appears. Now, this seems to be more useful constraint, except that this is yet not completely useful because we have not specified what alpha is. If we can actually bound alpha, then it will be useful. But the positive thing I can say is that these conditions have been tested by many examples, and Timo Weingart, who is sitting in the front, has been right. He has made heroic effort to enumerate many examples, and but no counterexample have been found so far. And but as I said, we can have even sharper and useful constraint on low energy theory if alpha can be bound. And so that's what actually I'd like to talk at the first part of this talk. Okay, so before we go into that, there is the ADS-CFT version. I would like to note that there is the ADS-CFT version of this conjecture. And this was formulated by Eric Perlmutter and the collaborator in 2011. And 2020. And so there, you directly identify moduli space of gravitational theory with conformal manifold and formulate the claim in the language of conformal manifold. So the conjecture one is that all points with higher spin symmetry are at infinite distance point. And the conjecture two is converse, that CFT at infinite distance always have higher spin point. So this conjecture one has been proven even in the original paper in supersymmetric theories. And then last year, Baum and Calderon Infante actually proved this for any formal field theory. And so I heard about this work last summer, very impressed, and I thought, well, I should work on it. So I worked on it for about a year, and I'd like to report on the result. We were able to find, so in this work, still there was no general constraint on alpha. So with Yifan Wang, we tried to improve the situation. We have not been able to do it for all the ADS, all the dimensions, but in the case of ADS3 CFT2, we are able to produce rather sharp bound. So here is what we proved. So first is that if there is a geodesic on the conformal manifold, along which conformal dimension vanishes in some limit, the homological distance to that limit is infinite. And in that limit, the conformal dimension vanishes exponentially as expected from the distance conjecture, and we can put upper bound on alpha. And the third statement, this is actually a sort of refinement of the conjecture by Konsevich and Soiberman, that CFT in the limit contains subalgebra of local operators described by flat space sigma model. And the last conjecture is the lower bound. So alpha is bounded by square root of central charge, 1 over square root of central charge. So this coefficient is bounded between these two. And in fact, moreover, these bounds are sharp, that we have been able to identify the necessary and sufficient condition for saturation and have example to saturate both upper and lower bound. So this was a mouthful. So basically, in this simple slide, I can say that the claim we made, what we were able to derive from first principle in CFT is that conformal dimension vanishes only at infinite distance, and when it happens, it's exponential, and the coefficients bounded by in this window. Okay, so it's interesting to translate this result in the language of gravitational theory. So when CFT, so by the way, I want to say that we proved this statement regardless of whether conformal field theory has holographic gravitational dual. So this is a property of conformal field theory. However, some conformal field theory has weakly coupled gravitational dual, and when it does, then we can translate this in the language of gravitational theory. And so that this bound, upper bound and lower bound of alpha can be translated into bound between Planck scale and ADS radius scale. So what this means is that the tower, the lower bound means that tower of light particle must emerge when scalar field travel greater than Planck scale. So this was actually originally what we wanted to say in my paper with Cumrun. We wanted to say that when scalar field has flat direction and if it travels greater than Planck scale, then the tower of light particle must emerge. But we cannot, at that time, we'll only be able to say that order 1 number in the Planck unit. But in this work, we are actually be able to nail this number to be square root of 3/2. And we also, this upper bound means that the light particle can emerge when scalar field is greater than, probably greater than ADS scale. But that's a big distance. And those are the two conditions. And in supersymmetric case, it's interesting because there we will see, probably if I have time, I will explain, but you can actually sharpen the, strengthen the conjecture, and it becomes like that. And interestingly, this matches with the sharpened distance conjecture. This was actually can be deduced from citation of postphone. I think, in fact, this is a work for which the Frontier Prize was given to Wolfgang Hirosi and Timo Weingarten. And but there is also a recent paper by these people, and it matches with this, but in 6 dimensions. And I think the idea is that, well, in the case of ADS 3 times S3, if you take the limit where you can recognize the flat space limit, this matches up. But there is actually a puzzle because there is also a 5-dimensional example of Maldacena, Strominger, Witten, where ADS 3 times S2. And if you apply this in that case, actually you can get a bound that is actually sharper than what you would expect from sharpened distance conjecture. So there is actually some puzzle about this that maybe at some point we can discuss. So I think I'm a little bit getting short of time, so I'm going to skip this. But here in this slide, I spelled out the assumption that we made in proving this statement. So basically, the main assumption is that 4-point function and the light operators are well defined in the limit. But some of the theorem can be proven in a weaker assumption. For example, the first 2 statements do not assume existence of local stress center because we only use global conformality theory. So these can be easily generalizable to higher dimensions, I think. And so this third claim does not even assume that there is a continuous parameter. So even if you have a discrete family of conformality theory, the limit is always contains some flat space sigma model. So for example, the large level limit of Wess-Zumino-Witten model is a flat space conformality theory. So this is an example of that. Okay, so this is the reminder, the plan of the reminder of the talk. So I'll discuss some example and prove first 2 statements and prove second statement and discuss more constraints. Okay, so the first example, so sigma model on flat torus. So this is a well-known example. So you have the Zamolodchikov metric. So this moduli space has 2 types of singularity. One is the orbifold singularity, and this is at finite distance, and indeed the gap does not vanish. But on the other hand, there is the infinite distance limit where you can, and then you can measure, you can calculate the gap of the conformal dimension. Indeed, it decays exponentially in the Zamolodchikov distance. And since the exponent is 1, so that means that alpha equals 1. So it saturates the upper bound. Calabi-Yau sigma model is more interesting. So because there are more variety of singularities. So in the case of quintic, for example, there is a Z5 orbifold point, which is also known as Gepner point. And in this case, there is a gap, and we can identify what kind of field saturates the gap. Conifold is even more interesting because there, actually, if you look at the spectrum of conformal field theory, in the limit where you go to conifold, there is actually continuum spectrum coming down. But it doesn't go all the way to 0. It stops at the finite value, which according to recent paper by Shi-In and the collaborator is exactly 1/2. So therefore, in this case, actually, the conformal dimension does not go all the way to 0. And indeed, the distance to that point is finite. So it agrees with the expectation. There is, of course, large volume limit, which is at infinite distance. But interestingly, compared to this Zamolodchikov metric of torus, there is actually, if you do the calculation carefully, there is a factor 6, which means that alpha is actually 1 over square root of 6, which is less than 1. But it's greater than 1 over square root of central charge. And if I have time, I will explain actually, this 6 is actually a very natural number. And so I will explain where it comes from. Here I have some example of non-unitary conformal field theory where some of the assumptions violated, and indeed the theorem is violated too. So, but I'm not going to, in view of time, I'm going to skip this example. So I'm going to first prove the first two statements, which is that it takes infinite distance to reach the limit. And in that limit, the conformal dimension decays exponentially, and this coefficient is bounded by 1. Okay, and so here is a proof. Okay, so I'll first with start with the case when there is only one exactly marginal operator. And if we understand this case, then generalization to the case with more marginal operators is easier. So by assumption, there is a primary field whose conformal dimension vanishes at some point on conformal manifold, and in some limit on conformal manifold. So that's the assumption. And so suppose there is such a primary operator, then suppose we can choose a geodesic coordinate so that near this, at least near the point where delta vanishes, where delta monotonically decreases toward the point, and it satisfies this renormalization group equation. I think I first saw this in the Morozhikov's paper. And so from this equation, you can easily see that the distance to the limit where delta vanishes is infinite if this 3-point function OOM vanishes at least linearly in delta. And in fact, I'm going to show you in the next few slides that we can prove stronger statement. The 3-point function actually not only decays linearly, but coefficient is equal to 1 in this case. Okay? So how do we prove this? We're going to use global conformal symmetry. So because of this global conformal field theory, if you have an operator whose conformal dimension vanishes, if you take derivative, you get an operator J with square root of delta, where J becomes 1, 0 operator in the limit, where delta vanishes. Because of this square root, this 3-point function is related to JJ bar and M with the extra factor of delta. So what we want to show is that JJ bar M is equal to 1 in the limit. That's what we want to show. Now, depending on how much time I have two sets of proof. One is non-rigorous and quick and intuitive, and second is more careful. So let me first give a simpler and non-rigorous derivation, and after that we can see how much time I'm left, and then decide whether to give you full proof or not. Okay, so let's present a simpler and less rigorous proof. Okay, so the idea is we are normalizing this original primary field with normalization 1 in the 2-point function. And if you have that, and if you use this definition of J, then we can calculate 2-point function of JJ, J bar, J bar, JJ bar in this case. And JJ bar has delta in it, which means that in the limit where delta goes to 0, J and J bar decouple. Okay, so I transcribed this important 3 equations up here. And then what I'm going to do is to do the conformal bootstrap. So this is non-rigorous derivation. So let's consider J bar J, J bar J. And suppose I look at the T channel, which is the channel where W goes to U and Z goes to V. So in that case, the leading singularity is the identity operator, and it gives you 1. And then there are other contributions. But we can also look at S channel where you can consider JJ bar, Z goes to W, so JJ bar singularity. So that gives you delta times this one. So it gives you this contribution. But in this channel, we may also consider a contribution of marginal operator, which gives you this conformal block times CC bar M squared. And I was very happy when I realized that these two functions are identical. Because that means that in the limit for delta goes to 0, this vanishes. And this can be identified with this one. And if we can argue that the other part, which comes from other exchange of other operators, are linearly independent of this function, then we can basically say that Cjj bar M square is equal to 1 in the limit. So that's the idea of the proof. That is that by crossing symmetry, by identifying T-channel term here, T-channel identity exchange, and S-channel marginal operator exchange, we can say that Jj bar M is equal to 1, and therefore coefficient is 1. So I think I only have 20 minutes left, and I still have more than half of transparency. So unfortunately, I cannot, unless there is a question after, I'd be happy to stay and answer a question, but I know there is another speaker in 15 minutes after my talk, so I should be fair to that speaker. So I'm going to skip the rigorous proof. The point of rigorous proof is basically to make sure that we can project out this dot path. We actually are going to construct explicit projection operator. So this is our projection operator, which projects out any term in this dot term, so that we can actually rigorously prove that the Cj bar, Cj bar m is equal to 1. So this is what we did. I was about to do. So I'm happy to go over this with you if any of you have questions later. Okay, once we prove this, it's very straightforward to generalize it to more a case where you have more than one marginal operator, because in that case, basically what happens is that this term, instead of exchange of one marginal operator, you have exchange of many marginal operators. So basically, the identity you get is that sum of square of Cj bar m over all possible marginal operators sum up to 1. That's what you get. And so this is this equation. So from that, by using some simple linear algebra, you can prove that you can still have this exponential linear behavior, but alpha is bounded by some number which is less than 1, where absolute value of alpha can be less than 1 because the sum of the operator may be marginal but not exactly marginal. And so when all the operators are exactly marginal, absolute value of alpha is 1. But you can also have, if you have multi-moduli case, you can choose to go in the limit in non-economical paths. So the cosine theta is the angle between the direction of steepest descent of delta and the general direction. So in general, alpha is less than or equal to 1. So this is the result. So this is a proof of the first two statements. So let me go on to the proof of the third and fourth, which is that the limit contains always some flat space sigma model, and alpha is bounded by 1 over square root of c in that case. Okay, so in general, if you take the limit, so to prove this, I would like to make this observation that in general, if you take the limit when delta goes to 0, not only one primary operator vanishes, but you can have several primary operators whose conformal dimension goes to 0 simultaneously. I'm not assuming that there are many of them or there are infinitely many of them, but supposing there are several of them, for each one of them, you can define Jn. And these Jn are linearly independent before you take the limit because these operators On are linearly independent. But if you take the limit where delta goes to 0, then there might be relations and they may not be linearly independent. So before we do anything, we want to find out whether there are any relation between J's. The only relation that we know of about these primary operators are operator product relations. So let me write down the operator product relations. So I guess this one, oh yeah. So there is operator product relation of O and O, and I assume that there is a 3-point function like that. If we have several of such operators, they may have OP among themselves, but there are also contributions from conformal weight operators whose conformal operator does not vanish in the limit. You can easily see that you can separate out their contribution. So now suppose you have such OPE. So you can actually derive the relation between J in the following way. Suppose I take sum of derivative operator of Z and W acting on this. On the left-hand side, you get this. On the right-hand side, because of this singular part, it's a difference and this is sum. So you only get this type of relation. So basically, you get the linear relation. And we argue that these are all the linear relations. But you can also get quadratic relation. If you take the derivative of Z multiplied by derivative of W, then you get actually quadratic relation. And you get the double pole and single pole. And you see that it looks like Hatsumodi algebra. And so, in fact, from this, you can argue that, well, you can easily see that because of the consistency or associativity of the algebra, this 3-point function must be controlled by structure constant of a compact group associated to the Kac-Moody algebra. But because the mass gap has to vanish, and because conformal dimension primary operator of compact Kac-Moody algebra is gapped, so therefore, in the end, you can prove that you only have abelian Kac-Moody algebra. And from that, you can bosonize it, and you can deduce that the limit always contains flat space sigma. Flat space sigma model with the target space Rn has conformal dimension n, so therefore n has to be less than C. Okay? So basically what we show, this shows is that in the limiting CFT is locally this flat space sigma model times compact conformal field state. But I would like to caution that this is not actually global direct product, and this was actually cautioned by Edward too. So I thank you very much for pointing out this subtlety. And in fact, there are no, examples with non-trivial global structure. So I give you two examples. There are more. So let's first consider this Z2 orbifold of a circle. And in that case, there is a primary operator which is given by cosine. I have to have cosine because this operator is invariant and the x goes to minus x. So this is Z2 invariant. Now, if you take derivative of operator with respect to z and define j, then you get to not only del x, but in fact O tilde, and O tilde is sine. Now you say that where x r goes to infinity, if you take r goes to the infinity limit where it's the infinite distance limit of this orbifold, you say that On would vanish because you have sine and r goes to infinity. But it is not. In fact, it's more subtle than that. You can show that this On is actually a topological operator, dimension 0 operator, which is endpoint of topological defect line that implements quantum Z2 symmetry. It was shown by Cumrun Vafa in 1988 that if you consider orbifold, by gauging some discrete group symmetry of conformal field theory, then in orbifold theory, you get a new quantum symmetry. And there is a topological defect line which implements the symmetry, and that is endable. And On is actually operator which sits at the endpoint. And so this is actually non-trivial operator in the end. So in this case, you can see that the flat space limit is not just x, but it always comes with this topological operator. There is also another very interesting example, which is a k goes to infinity limit of a k-type Virasoro minimal model. So it's a diagonal minimum model, and you take k goes to infinity, and you get C equal 1 sigma model. So there was actually a very interesting work by Runkel and Watt in 2001, where they actually studied this limit and found some interesting structure, and they found that it looked like there is a very flat space sigma model in one dimension, which is reasonable because C equal 1 theory is like that. But more recent paper by Mazzero and the collaborator shows more detailed structure of this, and they found actually that not only you have this flat one-dimensional target space, but there is actually a pair of walls where there is a non-trivial profile of tachyon and dilaton. And distance between the wall becomes infinite in the limit of k goes to infinity. So basically, you have just one wall. So generic point in target space is just flat space, one-dimensional flat space, but there is actually a defect. So this is another example where CFT is locally a flat space sigma model times compact CFT, but globally there are some other structure. And so now I'm running out of time, so I'll go a little bit faster. So basically, by knowing the structure and, of the limit and by knowing the classification of marginal operator, we can actually calculate the coefficient alpha in terms of this structure. And you can actually derive the lower bound in terms of 1 over square root of n, which is bounded by 1 over square root of c. So this is a derivation of the lower bound. So to summarize, we show that the delta can vanish only in the infinite distance limit in conformal manifold. And there, when it happens, the gap decays exponentially and the coefficient is bounded like that. And in fact, the large volume limit of quintic Calabi-Yau manifold saturates this lower bound. So I said that it was mysterious that the alpha is 1 over square root of c in the large volume limit of quintic Calabi-Yau. But this can be explained as the lower bound here, because the C is 9 for Calabi-Yau sigma model, and it's 1 over square root of 6. And as I said before, that if CFT has a holographic dual, then it can be, these quantity can be translated in this way. Okay, so I have 10 more minutes, so I will go quickly about other constraints. So the other constraint is absence of global symmetry, which quantified to be weak gravity conjecture. Again, just like in Einstein's autobiography, the first earliest second Swampland condition that I can trace was this paper by Misner and Wheeler. This is where the paper where they discuss geon. And in this paper, they essentially say that there is no global symmetry in quantum gravity. Now, often attributed to John himself, but first paper. So I imagine maybe if there is people who are familiar with history of general relativity, probably they can give us insight. But probably John Wheeler was talking about it in other places also. So to prove this, I used so this is actually citation of this award, and for this we use the ADS-CFT correspondence. And in particular, important thing is generalized Neta theorem, which again we learned from Edward. So for both of these work, actually we owe Edward for the very important advice. So this is a beautiful paper by Bookport, Dubrusha, and Longo, where they consider generalized notion of Neta theorem. So Neta theorem says that if you have continuous symmetry, there is a Neta current, and symmetry, the unitary operator implementing symmetry is the exponential of integral of Neta current. So from this, it automatically follows that if R is the union of these joint subregions, then this unitary operator which implements the symmetry is a product of operator associated to each region. Basically, this generalized Neta theorem of these people claims that the same thing happens for a finite group under some assumption about quantum field theory. And another thing we use is the entanglement wedge reconstruction. Fortunately, Shidon got award for this. I'm assuming that he's going to cover this in his talk. So I'm going to skip the discussion of this. And from this, we are able to prove this. So if there is so the contrary to the claim of absence of global symmetry, if a gravitational theory has a global symmetry, there must be a bulk operator that transforms faithfully into another local operator. However, if the symmetry generator is a tensor product of symmetry generator associated to each region, and if you define the boundary in some small regions, then the entanglement wedge for a union of entanglement wedge associated to this region never attach this operator in the middle. So therefore, commute with a local operator in the bulk, and that is a contradiction. More information theoretical way of saying it is that basically that ADS-CFT correspondence tells you that the information deep in the bulk is reconstructed by the entanglement or in the long-range entanglement in the boundary. However, symmetry generator, because of this Neta theorem property, does not change the long-range entanglement of the boundary because you can divide this unitary operator in pieces, and each of them acts unitarily only locally. So therefore, for example, it does not change the entanglement nature between here, this region, and this region. And that is basically the reason why this unitary operator cannot have non-trivial commutation relation with the operator in the bulk over here, because this operator cannot change the entanglement property of the corresponding boundary state. So this is sort of the derivation. Okay, so we have some comment, but in view of time, I'm going to skip. We are also able to prove the completeness of gauge charge, which is that not only the global symmetry is not possible and it has to be gauge symmetry, but all possible unitary representation for that symmetry appears. Okay? Again, this by itself is not a useful constraint because we don't know how this symmetry is broken. So for example, standard model particle physics preserves B minus L symmetry, but it can be violated or gauged in high dimension. So this is analogous to the absence of non-dynamical parameter discussed earlier. That what seems like a non-dynamical parameter may be expectation value of a dynamical field fixed by the potential. You can think of this as a sort of -1 form version of absence of global symmetry. So that leads to the weak gravity conjecture. And we have some, in our paper, we have some discussion of how we go about proving this weak gravity conjecture. So this is basically what I wanted to say in this talk, that there is this very sort of old idea of absence of arbitrary parameter and absence of global symmetry, which are now quantified in a sort of more into a more stronger statement, like distance conjecture and weak gravity conjecture. Both of them are sort of supported by a very robust set of examples from string theory construction. But now we are at the time when we can actually roll up our sleeve and try to actually prove some of these statements, and we have succeeded in doing that, at least in this case, for ADS3 CFT2. Now, in the remaining 5 minutes, I'd like to say a little bit about scalar field with potential. This is not my work, but this is so interesting, so I would like to tell you about it. So far, so for example, in the distance conjecture, we assume that there is no potential here. But supposing you have potential here, then for example, Cumrun Vafa and my collaborators have some conjecture about it. And so it will be interesting to see whether some of this is true. But there's actually something you can actually derive from first principle in the context of ADS-CFT correspondence. And that makes use of Penrose inequality. So in the flat space, Penrose inequality was motivated by cosmic censorship hypothesis. But in ADS, it's actually a theorem that this is an inequality that can be proven by consistency of conformal fields. There is a beautiful paper by Gary Horowitz and Netta Engelhardt. And there are actually the inequality is slightly deformed from flat space limit, because flat space Penrose inequality is the inequality between mass and square root of the area of apparent horizon. But there is this correction term in ADS. But if you include that, then this is something you can actually prove from consistency of conformal fields. So the interesting observation is that this Asmund Fogstad a couple of years ago, where he pointed out that depending on the type of potential, actually you can actually produce the initial condition in some Cauchy surface, which violate this condition. So therefore, such potential should be in swampland. In fact, this is actually a rather big space. So for example, in this particular parameterization of the scalar potential, this coefficient G5 and G4, there is this exclusion region in the graph of G3 and G4. And so if you are in this region, you can actually construct Penrose inequality violating initial conditions. So these are in swampland. Okay, so summary and future programs. So I wanted to point out again that there are constraints in low energy effective theory of gravitational system that cannot be captured by the standard Wilsonian paradigm. And indeed, I think these two statements are more or less theorem now, at least in the context of ADS-CFT. And so we can try to quantify them, and we are in the process of proving and putting constraint on some of the parameters in here. And in ADS, therefore, we can quantify and prove part of this conjecture. And so there are, of course, future programs. First is actually, this is the first thing I want to do, which is to consider converse of this distance conjecture claim, which is that the spectral gap always vanishes in the infinite distance limit. And then we also, this is also achievable in the next few years, I hope, which is to derive bound on alpha in higher dimensions. There is a very interesting observation that actually Cumrun and I made in my distance conjecture paper about constraint on topology of conformal manifold. And Sergio Cecotti tells me that you can actually prove them at least with sufficiently large number of supersymmetries. There is actually seems to be a close connection between the distance conjecture and weak gravity conjecture, and it would be interesting to explore that. And of course, we'd like to eventually understand how all this can be used to understand the flat space limit, or even space with positive vacuum energy. Thank you very much for your attention.
Your very nice talk. Questions?
This question you raised at the beginning of whether a modulus of a CFT is always related to a local operator seems to be related to the question of whether the modulus can be spatially dependent.
Yes.
Do you have a way, by analogy of the methods used before, to show that you can make the modulus spatially dependent?
So far, this is what Yuya and Shota, this is work in progress, but I guess it's recorded, but I will tell that anyway. So we are able to prove that suppose you have a pair of conformal field sets. If there is a domain wall which connect these two pair of conformal. So suppose there is a family of continuous family of conformal field theory. If you can construct a domain wall relating conformal field theory, connecting conformal field theory with different parameters, from that we can actually reconstruct the exact imaginary operator which implement the transformation. So this is sort of a more refined version of your question of whether you assume this. And so we are now in the process of actually proving that, which is to say that when you have a continuous family of conformal field theory, you can actually always construct such interface. Yes. Right. So which conformally invariant, the conformal domain wall, preserving half of conformal symmetry out of the domain. So we are in the process of proving that, and once we prove that, then I think we would have deduced it.
Other question?
Yeah, I wonder what happened to your lower bound when the central charge is smaller than 1?
So in that case, there is no moduli space. I don't know of any example of conformal field theory with C less than 1, because when C is less than 1 conformal field theory, we know everything. We actually know all the unitary conformal field theory. They don't have any moduli. So I said that there are counterexamples in non-unitary. This was the point of this slide, that I showed that well, I cannot go all the way there, but if you have non-unitary theory, then some of the theorems are violated. So non-unitarity is not the assumption. Yes, you can actually have non-unitary theory C less than 1 with moduli, which violate the distance conjecture. So yes.
Okay. Other question?
Yeah, so I think in order to prove this, we have to do some minimization of domain wall with respect to some quantity. Yes, it's not, but we are not assuming supersymmetry. So yes, but in some cases, in some sense, it's a lightest domain.
Other question?
Timo is raising hand.
Concerning your proof of the weak gravity conjecture, for ADS3CFT2, it was proven that there's actually a tower of super extreme.
You mean the distance conjecture, not weak gravity?
No, the weak gravity conjecture.
Oh, weak gravity.
In the second part, you also mentioned.
Our argument for the weak gravity conjecture.
Very good. So for ADS3CFT2, modularity of the CFT2 was shown to give rise to a tower actually of super extreme effect. Do you see any indication of that also in Heine?
Yeah, so good. So yeah, in fact, the ADS3CFT2, you can make some strong statement about this. I've been trying to think how we can generalize this higher dimension. I don't have a good idea so far.
Other question?
I have a naive question about, you said that you have don't have the global symmetry. Is that means the symmetry is only described by the operator locally?
Well, so locally is a strong word, so it can be black hole. So, but what I can say is that in the context of when you have a holographic dual, then you can have charged black hole or some other exotic state. But if the state has finite energy, if the energy of that charged state is bounded from above, then the size of the operator is bounded in ADS. So you can always take the boundary segment to be as smaller and smaller, so that it's always commute with such operator. So it doesn't have to be sharply localized. And in fact, you cannot have a very sharply localized operator. You have to do gravitational addressing. But for example, it can be like charged black hole. And but if the energy is finite, the size of the prize is finite. So therefore, you can always arrange so that the boundary unitary operator commute with the charged black hole.
Other question? If not, thank you very much.